Hello, we're going to talk today about space curves. As a first example, we have the straight line. Well, a space curve has this form. We usually represent it with R of t, a single input, a scalar input, and then we have three outputs in the form of one vector. So the output counts as one vector made up by three components. Each one of the components is a real valued function, f, g, and h, I'm calling them. We can also call them x, y, and z, respectively. Before we do advanced examples, think of this as a straight line. We already saw in previous videos that if each one of those is a linear function, then the curve that we produce is a straight line. When t is positive, it goes in one direction. When t is negative, it goes in a different direction, in the opposite direction. And that's it. That's a straight line. So a straight line is what we call a curve because it has this form. Before we move on to more twisted or curved graphs, let's review the graph of a circle in parametric equations. So let's just have a quick review of circles with parameter t, So this is going to happen in 2 dimensions right now, this quick review. So A, if we have x equals, say, 4 cosine of t, and then y equals 4 again sine of t, well, we're familiar with this graph. As t goes from 0 to 2 pi, we're going to have, of course, this is in 2D, a circle of radius 4. So the radius is going to be 4. When t is equal to 0, we start at this point 4, 0, 4, 0. And then as t increases in value from 0 to 2 pi, then the point that is drawn moves along the circle in the counterclockwise direction. So when t is pi over 2, we're up here, and when t is pi, we're here, and so forth. And then we complete this circle one time as we go from 0 to 2 pi. If we want to go around 2 times, then we go from 0 to 4 pi, and so forth. So that is an example. What happens if we invert those two? I'm going to try to squeeze that in this piece of paper. So if we invert, let's call this example B, if y is 4 times cosine of t, and x equals 4 times sine of t. So in example A, x was the cosine. Now y is the cosine. And again, 0 is less than or equal to t and 2 pi. In this case, we have the same circle. But when t is equal to 0, the cosine of 0 is 1 times 4 is 4. So y is 4 and x is 0. We start there. And because the sine, which is the x variable, increases as t goes from 0 to pi over 2 initially, the point that we are drawing is actually going to go to the right and down in this direction. So by inverting those two, we're changing the starting point. The starting point here is 4, 0 in A. In example B, the starting point is 0, 4. And we are going to go in a different direction. So this is a quick review of the circle. Example C, say you want to go in the same direction, clockwise direction as here. in this direction, but you want to start in the same point, 4, comma 0. That is easy to fix. What we can do is set y to be 4 times cosine. Start out with pi over 2 and add t. X would be 4 times sine pi over 2, add t to it. Again, t goes, or t is between 0 and 2 pi. And this causes us to have a circle in the xy plane starting at this point and going in this direction. So you can shift this one way or the other. And let's double check that when t is equal to 0, we have the cosine of pi over 2, which is 0. So y would be 0. Yep, that point has a 0 on the y value. So that is 4, 0. And then when t is equal to 0, sine of pi over 2 is 1 times 4 is 4. So x would be 4. So we're good. And then as t increases from 0, then we are beyond pi over 2, at which point the sign starts to decrease. And that's why the x value starts getting closer to 0. So we're good. Yep. Yep. So now let's go back to 3D. Back to 3D. So space curves. Yeah, this is a flat curve, not space. It is a curve on the plane. Now let's do curves in space. So let me label this as example 1. And we're going to have different parts of example 1, different circles. So example A, let's say r of t is 4 times cosine of t, comma 5, comma 4 times sine of t. So this is in 3 dimensions. Y value, this is the x value, the y value will be fixed at 5 while we are producing a circle around the y-axis. We're going to start with an x value of when t is equal to 0. Let's make sure we put down a domain from 0 to 2 pi. So when t is equal to 0, we have the point 4, 5, 0, because the sign of 0 is 0. Let's draw the picture. So we have a circle where this center of the circle is at 0, 5, 0. So let me put an arrow. 0, 5, 0 is the center of the circle. And then if we go this way, this point, which is our starting point, will be, let's see, 4, 5, 0. 4, 5, 0. And the cosine, which is the x value, is going to decrease. So remember, this is the x-axis. So then this is the y-axis. And of course, the z-axis. And the x value decreases, which means we're getting closer to the y-axis, while the z value increases. So we go up. And that means that the direction of this circle is this one. So we start here and we go up, going around this way, and come back to this point by the time we get to 2 pi. So this is a single circle that is vertical with center at 0, 5, 0, and the circle is going in this direction, kind of going from octant 1 to octant 2. Yeah, and then coming back to octant 1 as we finish the circle. So that is example A. What happens if we permute those, if we exchange those two? So example B, so this is example A. let's say we have that r of t is equal to 4 times sine of t, 5, 4 times cosine of t. So we have that. Then, still between 0 and 2 pi. We have the same circle, except that we're going to start with an x of 0. So we're going to start up here. Let's draw a new picture. Same circle, starting at the top, and going in this direction because the x value increases. So we're coming towards us, and the center of the circle is still at 0, 5, 0, but we start at 0, 5, 4 instead of 4, 5, 0. And then we go in this direction. Now, when I say we start at that point, what we mean by that is that that is the point obtained by plugging 0 into this equation. So 0 is a starting point. The real numbers don't really have a starting point because they go in both directions. But we're going to call 0 as the starting point, and then moving forward means going in the positive direction. And as we do that, we draw the same circle, the same exact circle, except that we start at different points and we go in different directions. This is kind of neat. And you can place the sine and the cosine anywhere you want it. Example C. So example C will be r of t equals, let's say we put 4 times cosine of t, comma, 4 times sine of t, which is a regular circle in the xy plane. But then we add 5 to our third coordinate. So the z value is fixed at 5. And then we have a regular circle on the x and y coordinates. When we draw this picture, we end up with this circle with center at 0, 0, 5. Our starting point is going to be, let's see, here. So this point will be 4 units this way, 0 units, and 5 units up. All of the points are going to have a 5 on the z coordinate because the 5 is fixed at the outset of the function. And then we go in this direction. So we're going to be going around this way. If there is no domain written, then that means that we have an implicit domain of all real numbers. So we start here, and then we can just go around 2 pi, 4 pi, 6 pi, and so forth. If I give, or if we provide a domain from 0 to pi, then we just have half of the circle. From 0 to pi over 2, a quarter of the circle, and so forth. You can draw anything you want in 3 dimensions, like so. If we have, as an example, d, r of t equals 4 cosine of t, 4 times sine of t, and 0 instead of 5, then we have the same circle in 3 dimensions, but down here. So this point will be going, this point is on the x-axis, this point is on the y-axis. This point will be 4, 0, 0, and this one is 0, 4, 0. And then there's There's nothing, there's no lift. We start at 0, we end up with 0 on the whole circle. This has a lift, a height of 5 units. So this circle is 5 units of the floor, while this one is on the floor, literally. If we put a -1, then we're going to be under the floor. If we put a -1 on the function. So those are different functions, and that's why we're labeled them as C, D, and so forth. Now, the next one is exciting. Um, it is going to be a helix. Let's say you have R of t. Oh, one thing I forgot to mention here is our starting point is this one, and we go in this direction. So if we view this from the top, from the z positive axis, then this is going to go in the counterclockwise direction. All right, so what if we have 4 cosine of t, 4 sine of t, and then t over 2 pi, which means that by the time t gets to 2 pi, this fraction will be equal to 1 unit. So that means that we're going to have a circle, if we view it from the top, because we have, in all of these cases, if you compare, this 2 the same as those 2, the same as those 2, and all of them are going to be the same circle as viewed from the top. Here, the height of the circle is 5, the height of the circle is 0. The height of the circle varies. So at first, when t is equal to 0, we have 0. But when t is equal to 2 pi, by the time we finish a whole revolution and we come back to this point, well, we're going to end up with this point, except that the height is going to be different. So let's draw it. We start here, we go around, and then we come back 1 unit above. So this is 1 unit above where we start. We start at 4, 0, 0, go all the way around with a circle-ish. It's actually a helix. Helix. And it goes around. And by the time we come back to the same XY position, we're actually 1 unit off the ground because we are dividing by 2 pi. Yep. So this is 1 unit. And then I didn't write down any domain, which means we can continue to go around. So if we do this one more time, I'm going to bump into my writing up here. But if we were to continue up here, we will come back another unit by the time we're lined up with this point. So there would be a point up here after we go around the z-axis, and this point would be 4, 0, 2. So this point down here, let's write down its coordinates, is 4, 0, 1. And every time you go around and come and lined up with the same point, we're going to end up with 1 more unit. So 4, 0, 1, go around 4, 0, 2, go around 4, 0, 3, go around 4, 0, 4, and so forth. If you go in the reverse direction, then we're going to go down here. And by the time we come back, we're going to be lining up here. And so this point would be 4, 0, -1. And that happens when t is equal to -2 pi. This point happens when t is equal to 0. This point happens when t equals 2 pi. Yeah. So this is a helix. And this is a standard helix. Oftentimes they put just t, but that stretches it out quite a bit. And then we end up with 6.28, which is approximately 2 pi. So this is a very stretched helix. So by dividing by 2 pi, we make sure that we only go 1 unit by the time we get to 2 pi. Yep. Yep. So this is fun. What I advise you to do to practice is to move those components around. So if you had the t over 2 pi in the middle, and then keep the cosine there and the sine, so exchange those two, what kind of picture will we have? We will have a helix, but it won't spiral up. It will spiral perhaps in a different way. It will spiral maybe, well, that's something you have to think. Um, if the t is in the middle, then it will spiral to the right. I already told you, I guess. If this t over 2 pi was here, then the spiral will come towards us to the right and up. So those are the three directions in which it can go. The one thing we also have to take into account, and we said it implicitly, is that the direction is this one. So we go up this way, which makes sense, I suppose, because we're going up. So that is the only way to go up on the curve. So we have a nice spiral, a helix. Um, yep, and then move those around, and that will give you a different kind of picture. All right. Example 2 is what is called a twisted cubic. Twisted cubic. It has equation r of t equals t squared, t cubed. All right. So if we look at this picture from the top, so if you just look at the x and y components, we have sort of x and x squared. If we label this as x, then we have x and x squared. And so the graph from the top, so this is a top view, is a parabola. Um, so the x-axis is here, the positive x-axis, and the y-axis would be there. And so we have a parabola. The reason why I'm doing it sideways, this is not conventional, is because what I'm doing is taking our space, x, y, z. So when you go up here, then the x is gonna, it depends, but assuming you go from the front to the top, then the x-axis is gonna be to our right. Yeah. Um, yeah, so that's why this looks unconventional, because I'm looking at it as if I was, oh man, this is gonna be hard to draw, but if I was here, there, then that, if I was a person here looking down at the space, that's what I would see. I haven't drawn the curve here yet, but it is a good idea to know what happens when you see the curve from 2 dimensions. Now, if you look at the xz point of view, or rather the y point of view, so if you look at the curve from this point of view, then we have a cubic. So this, um, so view from right side would be a cubic. Um, you know what? This is incorrect, because if I was, let me do this again. Um, if I was an observer looking at this from this side, the y values, then the positive x-axis would go this way. So I have to scratch this off, and the view would be this one, because the positive x-axis would be on our left. See, there's the x-axis on the 3 dimensions. If I was an observer on the right side, then what I would see is the positive x-axis on the left. The z-axis, the positive z-axis would be still up. But because this is unconventional, we usually have the x-axis on the right. Our cubic looks backward. That is very important. It's, some people ask me, can we do Calc 3 without pictures? And my answer is, if you can, let me know how, because I cannot do it without pictures. I have to draw many, many pictures to understand what is going on. So that is my answer. I Can you do calculus 3 without pictures? My answer is I don't know. If you find out, please let me know. All right. Now, if we look at this curve from the positive x-axis, so if the observer was here, where we are, but just looking straight into the axis, so if this is, we wouldn't be able to see this axis. We only see the y and the z-axis. So the view from this point of view, from the positive x-axis, would be something like x to the 3/2. Yeah, because if you put the t into here, you end up with z equals y to the 3/2. So the picture we obtain will be, well, this is the one picture if we take the square root, but we're going to assume we don't have. I'm jumping from here to here. But when we take the square root, we should have a plus or a minus, and that means we actually have this picture. All right. So how do we see this in 3D? All right. So we have a parabola that comes down, turns around, and comes back down this way. I actually made a model so we can see it. Okay, so this is the twisted, well, this is my attempt to a twisted, there it is, to a twisted cube. Okay, why? If you look at it from this point of view, let's see. Yep. From this point of view, it matches this graph. From this point of view, it should match this graph. It can probably twist it a little more, but I don't want to overdo it. From the top view, again, this is my attempt to the graph. It should be a parabola. Again, I can probably curve this a little more, but again, I don't want to mess with it too much. So this needs to be a little smoother and a little more curvy, but essentially this is what we end up with. It is a twisted cube of a function with a vertex where I'm holding it right there. Of course, I use a clip. So the picture, when you actually draw it, and after telling you how it looks, let's see, I'm going to draw a parabola, but then this is going to be lifted, so it's going to come down this way, and then if we put this point down here, it is going to come down this way. See, it is difficult to see. There's a curve here, and then comes back down, and that's what I'm trying to do here. The graph comes down, turns as a parabola. It goes, so pretend it's a parabola. From this point of view, we have a cubic, it S's. And from this point of view, we have sort of like a K. Yeah, the two legs of a K, the letter K. Yep. So there's our twisted cube. So play around with this. The equation, this is example 2. The equation, the original equation is t squared, t cubed. What I would advise you to do is to move those guys around, exchange those two or exchange those two, there's 6 different possible ways to rearrange them. So if t is here, we got 1, 2. If t is here, 1, 2. And if t is there, 1, 2. Yep. So there's 6 different ways to arrange them. do all 6 permutations and see what kind of picture you get, how the picture changes. Because we want to develop a little bit of intuition about how to graph those. There are other things we have to consider as far as this kind of functions. One is limits, and continuity. And continuity, they transfer in conjunction to the components, or they transfer to the components all in conjunction. So limits and continuity transfer to the components in conjunction. By the way, we're off the example. Now we're in general, in general theory. So if we have R of t equals f of t, g of t, h of t, 3 functions, 3 real valued functions. If you want to figure out whether this is continuous, so this guy will be continuous at t equals a, if and only if, so remember we use IFF to denote if and only if, those 3 are continuous at a t equals a. Yep. So the 3 of them have to be continuous. If one of them is not continuous, then the vector valued function is not continuous, any one of them. If any one of them is not continuous. So in order to have a continuous function, all 3 of them have to be continuous. Otherwise, this is not continuous. So that's the way we define continuity of functions. The limit is done exactly in the same way. The limit of R of t as t goes somewhere. I'm going to put a box because we could have limits to infinity. Will be the limit of f of t as t goes to the same place, the limit of g of t, the vector with this values as t goes to that same place, and the limit of h of t as t goes to that same place. If one of those limits doesn't exist, then the limit of the vector function will not exist. If this limit does not exist, it is because at least one of those limits does not exist. And we can leave it at that as far as the limits goes. Continuity, again, happens for the vector function if it happens to each one of the components and all of the components at the same time. All right, we're gonna stop the video here.